Hi everyone, myself B. Ramraj, Assistant Professor, Department of EEE, Andhra Engineering College, Erode. So in this video, we are going to discuss the topic named combinational circuits, right? Combinational circuit. So this is the topic which we are going to discuss under digital principles or digital logic circuits, right? Digital principles or digital logic circuits. So the first and foremost topic in digital logic circuits or in digital principles is this combinational circuits. So what do you mean by a combinational circuit, right? So combinational circuit is a circuit or a device which will perform some kind of arithmetic and logical operations with the help of a device called logical devices. Logical devices. So the logical devices is again technically named as logic gates, right? So logic gates. So if a circuit or an electronic circuit which has only logic gates to perform some arithmetic and logical operation, then the circuit is named as combinational circuits, right? So there are different kind of logic gates. Before we are going to discuss about the logic gates, let me explain the basic principle of this logic gates, right? So logic gates, the input and output of this logic gates are always zeros and ones, right? So the input and output of logic gate will be always of zeros and ones. Means the input and output variables are always represented by binary values, right? So digital means zeros and ones. Similarly, the logic gates always prefer or always use the input and output in terms of zeros and ones, right? So now let's discuss the types of logic gates, right? So types of logic gates and their corresponding logic symbols, right? So in this class we are going to discuss the types of logic gates and their equivalent symbols with corresponding expressions, right? Types of logic gates. The first and foremost type of logic gate is AND gate. AND gate. So the symbol for logic symbol for AND gate is this is the symbol for AND gate, and the input variables are A and B. We will be giving either 0 or 1 for A, similarly 0 and 1 for B. That is the input variables, right? Similarly, the output variable is Y. So the output of this AND gate will be the expression, the equivalent expression for this AND gate will be A is equal to A dot B. That is multiplication. Simply, in simple words, we can say it as multiplication, right? So this is the equivalent symbol for AND gate, right? So as I already told, the logic gates, all the logic gates will perform some manipulations with the help of binary values, binary inputs, and the corresponding output will be also in terms of binary, right? So this is the symbol for AND gate, and the Y is equal to A dot B is the corresponding logical expression for AND gate, right? In this video, we are going to discuss only about the logic gates, types of logic gates and their corresponding symbols with equal expressions. In next video, we will discuss the truth tables of this corresponding gates, right? So next type of logic gate is OR gate, right? So OR gate. So the symbol for OR gate is, normally we will have two input AND gate, OR gate, or we'll use based on the application we'll use 3 input AND gates or gates, right? So the input is not at all matter, right? We are available with two input gates as well as 3 input gates, right? But output is always one single output for the gates. So here for OR gate, the input is A and B, and the output is Y is equal to the expression or the operation of this OR gate is Y is equal to A plus B. This is addition, right? This is the equivalent expression for OR gate, right? So AND is multiplication and OR is addition. And the third gate is NOT gate. NOT gate. NOT gate is an inversion operation or a complement operation, right? So the input of NOT gate is 1 and the output of the NOT gate is also 1. Means that the input variable of NOT gate is either 0 or 1 and the output variable of the NOT gate is either 0 or 1. Based on the input, the output will be in the complemented form, right? Now look at here. The symbol for NOT gate is, right? It will have single input and single output, right? So if I give A as input to the NOT gate, the output will be in the complemented form. A bar will be the output. We can simply write it as Y is equal to A bar. Right? So I am denoting Y as a output variable for all the gates, right? To represent in a common manner. So next 4. So AND gate, OR gate, NOT gate. Next one is NAND gate. NAND gate. NAND gate. So the symbol for NAND gate is the same AND gate, but in output we will have bubble. Means inversion operation. Bubble means inversion operation, which is similar to NOT gate, right? So the two input variables A, B and output Y is equal to the output of AND gate is Y is equal to A dot B. The same output Y is equal to A dot B corresponding to this bubble, the output will vary as Y is equal to A dot B the whole bar. Complement, right? So complement of AND gate is NAND gate, right? Because we are using bubble the output side, right? Means bubble means not inversion operation. So Y is equal to A dot B becomes Y is equal to A dot B the whole bar, right? So next, number 5, NOR gate. So NAND gate is a combination of AND gate and NOT gate, whereas NOR gate is a combination of OR gate and NOT gate, right? So the symbol of OR gate you have seen already, but in the output we'll add a bubble for NOR gate, right? So input A, B, two input variables A and B, and the output variable Y, and the output for OR gate is Y is equal to A plus B, but I have used a bubble in the output of OR gate, so the expression will becomes Y is equal to A plus B the whole bar. Inversion operation of OR gate is the NOR gate, right? So next, number 6, XOR gate. XOR gate. XOR is nothing but X means exclusive, right? So 6 to 1 XOR and 7 to 1 XNOR gate, right? So exclusive OR and exclusive NOR, right? So what is this exclusive OR and exclusive NOR, right? Now let's see the symbol for exclusive OR gate. So exclusive or XOR. And this is the symbol for XOR. Input variables A, B, two input variables, one output variable Y is equal to. So the output or the equal expression for this or the operation of this XOR gate is Y is equal to A XOR B B. So this symbol is known as XOR, right? Plus the circle, plus over the circle is known as XOR, A XOR B, which can be also equal to A dot B bar plus A bar dot B. So here we got two product terms. If we get expressions like this, I mean A dot B, the whole bar, a product term, plus A bar dot B, another product term, right? So here A is in uncomplemented form and B is in complemented form. In this product term, second product term, A is in complemented form and B is in uncomplemented form, right? So if we get expression like this in a simplification of Boolean expressions, we can write this expression like this, A XOR B. So this is the equivalent expression for this corresponding two product terms, right? So these both are equal, right? So the ultimate aim of this XOR gate is we are reducing the number of gates, right? So in this for implementing this expression, we need three gates, right? One OR gate for plus symbol and A dot B bar on product term. Here we need an AND gate, and for this plus we need an OR gate, and this A bar dot B, so multiplication, we need one AND gate, right? So totally we need three gates, but the same expression can be implemented using this XOR gate with the help of A XOR B. So a single XOR gate is merely enough instead of preferring three gates, right? So the cost as well as the time, simplification time, these two are the major advantage of using XOR gate, right? So next, similarly, XNOR gate, the symbol for XNOR is input A, B, two input variables, one output variable, and the corresponding expression for XNOR is the inverse of XOR is XNOR, that is A dot B, right? So A dot crossover B, right? So this is the equivalent expression or equivalent operation of this XNOR gate, and this can be also written as A dot B plus A bar dot B bar, right? So you have two product term. One product term is in uncomplemented form. Both the variables A and B. Here there are two variables A and B. Both are in uncomplemented form. And in another product term, A dot B bar, A bar dot B bar. Both are in complemented form, right? So if we get expression like this, either one product term with complement form and another product term with uncomplemented form, then it can be written as A XNOR B, right? So advantage of both this XOR gate and XNOR gate is it will save time and it will save the cost by reducing the number of logic gates. So ultimate aim of an engineer or of an application, we need to reduce the cost as well as the time to perform a particular application, right? So these two gates majorly support in this parameters, right? So these are the 7 types of logic gates, right? So one more thing, NAND gate and NOR gate, these both gates are named as universal gates. So why it is named as universal gates, right? Because let us assume that we have NAND gate and NOR gate to implement a particular application or to perform an arithmetic or logical operations. We have only NAND and NOR gate. Assume this scenario, but we don't have the other gates like AND gate, OR gate, NOT gate, NAND gate, and NOR gate. Sorry, AND, OR, NOT, and XOR and XNOR. Right? We are having NAND and NOR alone in our hand. Right? So in this situation, we can perform or we can do the operations with the help of NAND and NOR, which and or not XOR and XOR does, right? So these equivalent gates operation can be done with the help of NAND and NOR gates, right? So even if you don't have these gates, with the help of NAND and NOR, we can implement all other gates, operations and manipulations, right? So that's all about the logic gates. In next video, we'll discuss the truth table for this logic gates. Thank you.